Somewhere beneath your feet right now, possibly thousands of meters beneath the ocean floor, there is ancient energy. Energy that powered civilizations, launched rockets, and heated homes across the globe. Getting to it is one of the most complex engineering feats humanity has ever achieved. Today, we are going on a journey. From the surface of the ocean all the way down to a reservoir of oil and gas that has been locked away for millions of years. This is the story of a single oil well and the incredible machine built to reach it. Before a single hole is drilled, something enormous needs to float out to the drilling location. This is the drilling vessel. There are two main types you'll encounter in deepwater operations. First, the drillship, which looks exactly like what it sounds. A massive ocean-going vessel with a drilling derrick mounted right through the middle of the hull. Drillships are mobile, flexible, and capable of drilling in water depths exceeding 3,000 meters. Second, the semi-submersible, or SEMI for short. This platform sits on enormous hollow pontoons that are partially flooded with seawater to pull the structure down and give it stability. Semi-subs are incredibly resistant to wave and wind motion, making them preferred in harsh sea conditions. Both vessels face one fundamental challenge: staying exactly in position while drilling thousands of meters below the ocean floor. Even a small horizontal drift could shear the drill pipe and cause catastrophe. The solution is called dynamic positioning, or DP. A network of GPS satellites, acoustic beacons on the seafloor, and wind sensors feeds real-time data into a computer. That computer then fires the vessel's thrusters, some pointing sideways, some forward, some backward, to hold the ship within a circle just a few meters in diameter, 24 hours a day, in storms, in currents, without anchors. Some older shallow water rigs do use anchors, but in deep water, the catenary of an anchor chain would be enormous. Dynamic positioning is the only practical solution. Now, let's go inside the vessel. Beneath the towering derrick is a gap in the hull called the moon pool. It is literally a hole in the ship, open to the sea below. Everything that goes down to the ocean floor, every pipe, every tool, every camera, goes through the moon pool. It looks terrifying the first time you see it. Water depth classification is fundamental to how a well is designed and what equipment is needed. Shallow water up to 300 meters. Here, jack-up rigs, platforms with legs that physically touch the seabed, are used. Simple, cost-effective, reliable. Deep water, 300 to 1,500 meters. Now we need floating vessels. The water pressure at 1,500 meters is roughly 150 times atmospheric pressure. Equipment must be engineered to withstand these forces. Ultra-deepwater, 1,500 meters and beyond. Some wells are drilled in water depths of 3,000 meters, nearly 2 miles of open ocean before you even reach the seabed. The world record at time of filming exceeds 3,400 meters of water depth. So how does the drill string, all those lengths of pipe, get from the rig down through miles of open ocean without being ripped apart by currents? The answer is the marine riser. This is a large diameter pipe, typically 50 to 65 centimeters in diameter, that forms a continuous sealed conduit from the vessel down to the wellhead on the seabed. Drilling mud circulates down through the drill string inside the riser and returns back up through the annular space between the drill string and the riser wall. The riser hangs from the vessel and flexes at the top and bottom using special joints. Without the riser, the entire drilling system would be exposed to thousands of tons of seawater pressure and lateral current forces. It would not survive. Let's take a full tour of the drill rig, starting at the top. That towering steel structure above everything else is the derrick. On a large offshore rig, it rises between 45 and 60 meters above the drill floor. Its entire purpose is to support the weight of the drill string. And on a deep well, that string can weigh hundreds of tons. At the very top of the derrick is the crown block, a fixed set of pulleys. Below that, the travelling block moves up and down, carrying the hook that suspends the entire drill string. The up and down motion of the travelling block is controlled by the drawworks, an enormous winch with a steel wire rope running from its drum, up over the crown block and back down to the travelling block. The driller can raise or lower the drill string by adjusting the brake on the drawworks. On modern rigs, the drawworks is controlled electronically from a driller's cabin. On older rigs, it was a physical brake lever requiring considerable skill and considerable strength. Below the travelling block, suspended from the hook, is the top drive. This is the electric motor, sometimes hydraulic, that rotates the entire drill string. It replaces an older system called the rotary table, which we'll discuss shortly. The top drive can spin the drill string at speeds from a few RPM up to 200 or more, depending on what is being drilled. It also lets drillers make up or break out pipe connections without stopping rotation, a major efficiency gain over older methods. Now we come to the drill floor, the heart of operations. This is where the crew works, where pipe is handled, and where connections are made and broken. Older rigs used a rotary table, a circular motor mounted flush in the drill floor that transferred rotation to the drill string via a hexagonal or square pipe called the Kelly. The Kelly slid through the Kelly bushing, a fitting in the rotary table, allowing the pipe to move downward while still receiving rotational force. The Kelly bushing fits into the master bushing, which drives the rotary table. Together, they form the torque transmission assembly. On modern rigs, the top drive has largely replaced the Kelly rotary system, but you will still see rotary tables and Kelly bushings on many rigs worldwide, and understanding them is essential. The people who work here, in hard hats, steel-toed boots, fireproof coveralls and eye protection, are the backbone of the operation. The driller sits in a pressurized, air-conditioned cabin at the edge of the drill floor, watching multiple screens and controlling every parameter of the drilling process. Weight on bit, rotary speed, mud flow rate, drilled depth. The driller is the pilot of this operation. The assistant driller works with the driller and monitors auxiliary systems. The roughnecks, or derrick and floormen, are the crew on the drill floor itself. They handle the drill pipe, operate the power tongs that make up and break out connections, guide pipe into the mouse hole, and operate the slips that hold the string suspended in the rotary table. One specific role deserves mention: the floorman, who positions and guides each new joint of pipe as it is stabbed into the previous connection. It requires precision in a noisy, physically demanding environment. High above, working the monkey board, a platform 2/3 of the way up the derrick, is the derrick man. When tripping pipe, the derrick man is responsible for racking back stands of pipe in the derrick. It is arguably the most dangerous job on the rig. Now we need to understand one of the most time-consuming operations in drilling: the trip. Tripping out means pulling the entire drill string out of the hole. This is necessary when a drill bit is worn out and needs replacing, when a logging tool must be run, or when a casing string is being set. On a 5,000-metre well, that means pulling 5 kilometres of pipe, stand by stand, out of the hole, unscrewing each connection, and racking the pipe back in the derrick or laying it on the pipe rack. A stand of drill pipe is typically 3 joints screwed together, roughly 27 to 28 metres. Pulling a stand, walking it to the mouse hole or fingerboard, and setting back, called racking back, takes a skilled crew about 2 to 3 minutes per stand. On a deep well, a complete trip can take 12 to 24 hours. Tripping in is the reverse, running the pipe back into the hole. Each stand is picked up from the rack, stabbed, made up with the iron roughneck or power tongs, and lowered into the well. Every trip is a risk. Every connection is a potential leak. Every hour of tripping time is an hour not drilling. Crews train for months to become efficient at trips. Drilling mud is the unsung hero of the well. This engineered fluid, which can be water-based, oil-based or synthetic, does several critical jobs simultaneously. It cools and lubricates the drill bit. It carries rock cuttings from the bottom of the well up to surface. It applies hydrostatic pressure to the formation, preventing fluids from entering the wellbore uncontrolled. And it stabilizes the borehole walls. The mud is pumped down the inside of the drill string to the bit, where it jets out through nozzles, picks up cuttings, and travels back up the annulus, the space between the drill string and the borehole wall, to the surface. At surface, the mud passes over the shale shaker, a vibrating screen that separates cuttings from fluid. The cleaned mud returns to the mud pit, is reconditioned with additives, and is pumped down again. A continuous loop. The mud engineer monitors density, viscosity, pH, and chemical composition constantly. Getting the mud wrong can cause wellbore instability, stuck pipe, or a blowout. The well officially begins the moment the first hole is made in the earth. This moment is called spudding in, and it marks the start of a journey that may take weeks or months. The first structure installed is the conductor casing, a large diameter pipe, typically 30 to 36 inches in diameter, that is either driven or drilled into the seabed and cemented in place. The conductor establishes the foundation of the well and prevents the shallow, unconsolidated sediments near surface from collapsing into the borehole. From this point forward, every subsequent casing string is installed inside the previous one, like a set of nested tubes, each cemented in place. Here is the architecture of a well. Imagine you're looking at a cross-section of the earth. After the conductor, the next hole is drilled, slightly smaller in diameter, and the surface casing is run and cemented. Surface casing protects freshwater aquifers and provides a foundation for the blowout preventer stack. Then comes intermediate casing, run to manage abnormal pressure zones, unstable formations, or lost circulation zones encountered in the middle of the well. Finally, the production casing, or liner, is run to the target depth through the reservoir zone. This is the innermost string. Between each casing and the borehole wall is an annular space. This is where cement is pumped. The cement job is critical. It must fully displace the drilling mud from the annulus, bond the casing to the formation, and isolate pressure zones from one another. A failed cement job can allow gas to migrate up between the casing and the formation, one of the root causes of well blowouts. Not all wells go straight down. In fact, the vast majority of modern wells involve some form of directional drilling. A vertical well is the simplest case. Drill straight down to the target. This works when the reservoir is directly below the surface location. But what if the reservoir is 3 kilometers to the side, or beneath a city, or beneath a nature reserve where surface disturbance is not allowed? This is where directional drilling comes in. Using a combination of a bent sub, a short-angled pipe section, and a motor-driven bit called a downhole motor, the driller can steer the bit along a pre-planned curve. The bit walks sideways through the rock, following a programmed trajectory. The ultimate version of directional drilling is horizontal drilling, where the wellbore enters the reservoir horizontally and can travel for kilometers within the pay zone. This dramatically increases contact with the reservoir and production rates. Almost all shale and tight oil wells today use long horizontal laterals for this reason. Measurement. While drilling, MWD tools transmit the bit's current inclination, azimuth, and position to the surface in real time via mud pulses, allowing the driller to navigate with precision. Beneath the vessel, sitting on the wellhead at the sea floor, is one of the most critical pieces of equipment ever engineered: the blowout preventer, the BOP. A blowout is the uncontrolled release of formation fluids, oil, gas, or both, to surface. It can mean explosion, fire, environmental catastrophe, loss of life. The Deepwater Horizon disaster in 2010 was partly caused by a BOP failure. It became the largest marine oil spill in history. The BOP is designed to prevent exactly this. It is a stack of hydraulically operated valves, some of which can seal around the drill string, some of which can seal the wellbore entirely, and the most extreme of which, the blind shear rams, can actually cut through the drill pipe and seal the well completely in an emergency. The stack also includes the choke and kill lines, used to circulate heavy mud into the well to overbalance formation pressure when warning signs of a kick, an influx of formation fluid, are detected. In deepwater operations, the BOP is controlled remotely from the rig via a hydraulic control pod. It can also be closed acoustically in emergencies from a device that sends a sonic signal through the water. After weeks, sometimes months, of drilling, casing and cementing, the drill bit finally approaches the target. The reservoir is not a cavern or an underground lake. It is a porous rock formation, often sandstone or limestone, where oil and gas are trapped between the individual grains of rock, held in place by an impermeable caprock above. Think of it like a sponge saturated with oil under enormous pressure. The pressure in the reservoir can be thousands of times greater than atmospheric pressure. This is the energy that, once controlled, pushes oil to the surface. The final production casing has been cemented through the reservoir. But there is now a sealed steel tube and a layer of cement sitting between the wellbore and the oil-bearing rock. We need to make a connection. This is done with a perforating gun, a tool run on wireline or tubing into the well. Inside the gun are shaped explosive charges, precisely positioned. When fired electrically from surface, these charges detonate simultaneously, punching a series of clean holes, perforations, through the casing wall, through the cement, and into the reservoir rock itself. These perforations are now the pathways through which reservoir fluids, oil, gas, water, can flow into the wellbore. The perforating operation requires careful planning. The depth must be exactly right. The orientation can be controlled. The density of perforations, shots per meter, affects the productivity of the well. Engineers model the expected inflow for months before the guns are ever fired. Once the well has been perforated and tested, the drilling rig's job is largely complete. The well must now be handed over to production. At the top of the wellhead, whether on the seabed or its surface, is installed a collection of valves, chokes, and pressure monitoring equipment called the Christmas tree. The name comes from the somewhat festive appearance of all the flanges and valve handles arranged around the central bore. The Christmas tree controls the flow of hydrocarbons from the well. Its master valve can shut the well in completely. The wing valves and choke allow flow rate to be controlled. Pressure gauges monitor the wellhead continuously. In deep-water subsea developments, the Christmas tree sits on the seabed. It is connected by flow lines and umbilicals to a floating production facility or to a pipeline going to shore. ROVs, remotely operated vehicles, perform inspections and maintenance. Somewhere beneath this ocean, through thousands of meters of rock, steel casing and cemented annually, through a perforated completion and a subsea Christmas tree, oil is now flowing. It moves up through the tubing string inside the well, up through the riser or flow line, up to the vessel or the FPSO, a floating production storage and offloading vessel, where it is separated from gas and water, stored in tanks, and offloaded to tankers. From there, it travels to refineries. It is processed into diesel, petrol, jet fuel, lubricants, and the thousands of chemical products that underpin modern life. Every drop of that fuel started its journey with a decision. Drill a well here, right here, through miles of ocean and miles of rock. The next time you fill a tank, or board a plane, or switch on a light, think about the vessel sitting on the water somewhere far from shore. Think about the crew at 3 in the morning, pulling stands of pipe in the dark. Think about the engineers who planned every millimeter of that borehole trajectory. This is what it takes to reach what the Earth has kept hidden for millions of years. This has been Into the Deep. Thank you so much for watching. I hope you found this presentation informative and enjoyable. If you did, please give this video a thumbs up and subscribe to the channel for more exciting videos and helpful content. Also, don't forget to check the attached document for this video presentation, where you'll find additional information and reference materials. Thanks again for your support, and I'll see you in the next video.